Let's start at the beginning. The very beginning, in fact. The Big Bang. In the Big Bang model of cosmology, the universe begins in a very hot and dense state, expanding over time. This expansion simultaneously cools the contents of the universe. In the early universe, ionized plasma radiated energy in the most powerful regions of the electromagnetic spectrum. As the universe has expanded, this radiation would be stretched out, or redshifted, down to a wavelength of about 2 millimeters. Once the universe expanded to a sufficient degree, ionized particles became far enough apart to fall out of thermal equilibrium, allowing the radiation to stream freely throughout the universe, an event cosmologists call decoupling. When we point our telescopes at the sky, we can measure the temperature of the radiation at the time of decoupling, also known as the cosmic microwave background, or CMB for short. The CMB is one of the most important cosmological discoveries in history and underpins much of our understanding about the universe. When we look at the CMB today, we're looking at temperature fluctuations, also known as anisotropies. An anisotropy is any region that has different qualities than its surroundings. In this case, the anisotropies are very, very small. The overall temperature of the CMB is around 2.725 Kelvin, and these fluctuations are on the order of 1 part in 100,000. It's hard to analyze these anisotropies by simply taking a look at the CMB. One way cosmologists have overcome this hurdle is by taking something called a power spectrum, which measures the relative contributions of anisotropies of different sizes to the patterns we see in the sky. From analysis of the power spectrum, cosmologists have learned about everything from dark matter, the content of our universe, its minimum size, its shape, and even its eventual fate. The CMB power spectrum is sensitive to at least 6 cosmological parameters, and even more information can be found in measuring the polarization of its light. That's why the most cutting-edge research in cosmology is making use of it. Powerful telescopes have been used since 1988 to map the CMB, with more advanced telescopes planned for the future. One of these telescopes is FYST, the Freddie Young Submillimeter Telescope. This telescope is being built at the CCAT site in Chile. Many institutions are involved in the development and testing of FYST instruments. Previous CMB telescopes, like the Atacama Cosmology Telescope, had detector counts on the order of 3,000. FYST is exciting because it will potentially have a detector count of over 100,000, making it one of the most sensitive ground-based telescopes ever deployed for the frequency ranges it will measure the sky in. These detector arrays are being tested in Michael Niemack's lab at Cornell, with the goal of first light, or the telescope's first usage, happening in 2025. Cosmologists hope that these new measurements will continue to unlock secrets within the CMB, helping us understand the universe and our place in it.